After studying this module, you shall be able to learn about the reactivity of dinitrogen as ligand in metal complexes, the classical metal complexes of dinitrogen, various methods of preparation of dinitrogen complexes. Introduction. As we have seen, the discovery of dinitrogen complexes such as pentamino dinitrogen ruthenium dianion, where anion is bromide, iodide, and hexafluorophosphate or tetrafluorophosphate in 1965, and the subsequent finding that it can be prepared directly from dinitrogen gas led most of the chemists to accept that dinitrogen complexes of transition metals are involved in biological fixation of dinitrogen. Extensive researches have been carried out on the preparation of dinitrogen complexes, and their reactivities were analyzed along with coordination ability of the dinitrogen with almost all of the transition metals. It was eventually found out that these complexes can act as intermediate in dinitrogen fixation. However, like the organic diazonium salts, the dinitrogen complexes are of substantial interest and have already showed to be valuable synthetic intermediates. Up to now, a large number of transition metal ions have been utilized for the synthesis of dinitrogen-based metal complexes. We are summarized these metals in the form of a table here. As we can see, the unshaded regions of the table shown here represent the elements that have been reported to form mononuclear dinitrogen complexes. So in the table, we can see metals that form dinitrogen complexes. The position of the metal ions in this table is significant in a number of ways, and a number of inferences can be made out. For example, this data closely coincides with the borderline regions between class A and class B metals, which were defined by Arland and Chart. Most of the metal ions forming mononuclear dinitrogen complexes also coordinate with carbon monoxide, which represents a bonding similarity between the dinitrogen and carbonyl as ligands. This table includes iron and molybdenum, which are believed to be active sites in nitrogenase complexes. Iron and molybdenum are being commercially used as catalysts in Haber's process for ammonia synthesis, which is very well known. A large number of dinitrogen complexes are known till date. A few of the examples are shown here. Most of these complexes are applied for artificial dinitrogen fixation. The first example of dinitrogen complex which is pentamino dinitrogen ruthenium dianion, was separated from the reaction of ruthenium trichloride with hydrazine in the aqueous solution in the presence of different anions, while the complex tris-triphenylphosphine dinitrogen cobalt prepared directly from dinitrogen gas. Here we can see three most important dinitrogen complexes. The first one is the first example of transition metal based dinitrogen complex, which was synthesized in a lab. The second cobalt example is the first example of transition metal dinitrogen complex derived from molecular dinitrogen, whereas the third one, the molybdenum complex, is the first example of molybdenum dinitrogen complex. These complexes were later used for artificial dinitrogen fixation. The revolutionary Haber-Bosch process was believed to involve the adsorption of dinitrogen as nitrogen atoms in the active iron catalyst at high pressure and temperature. In a nitrogen metal complex, a large number of ligands can coexist with dinitrogen on that metal ion. Other ligands that can coexist with dinitrogen in a metal complex are phosphines, halides, hydrides, ammonia, carbon monoxide, and even water. Moreover, the dinitrogen fixation bacteria, the metalloenzyme nitrogenase, catalytically convert nitrogen to ammonium ions. The active sites of these bacteria contain iron, molybdenum, and sulfur. Inspired by this, a large number of iron and molybdenum have been synthesized and research in and under process to develop efficient iron and molybdenum based artificial catalysis. A number of examples based on iron, molybdenum, and titanium of dinitrogen complexes are shown here. Here also we can see the dinitrogen fixation reaction by dinitrogenase, which involve the dinitrogen molecule 8 H plus ions, 8 electrons in the presence of magnesium ATP at 1 atm pressure and room temperature. And the product of this reaction are 2 ammonia molecules, 1 hydrogen molecule, and we get back 16 magnesium ADP complexes plus 16 phosphate units. Now we know what are dinitrogen metal complexes and their presence in natural systems. We also know how the natural dinitrogen metal complexes looks like. Based on this knowledge, scientists have developed a number of methods of preparation of dinitrogen metal complexes. Presently, there are many methods that have been developed with different metal ions. For example, the various preparations of dinitrogen complexes can be obtained by directly using dinitrogen gas. For example, the tris triphenyl phosphine dinitrogen cobalt, ruthenium, or iron based complexes can be simply prepared by the reaction. Here we can see that this tris triphenyl phosphate metal complex reacts with dinitrogen ligand and one of the hydrogen molecule is knocked out of the complex. The reaction is exciting because it may provide a model for the first step in the fixation of dinitrogen by dinitrogenase. The enzymatic reaction is competitively inhibited by dihydrogen, which is consistent with the rapid equilibrium reaction between a polyhydride and dinitrogen to give a dinitrogen complex. Similarly, dinitrogen can be added to various metal complexes, such as the titanosine dimer can be added to dinitrogen, forming a dinitrogen titosine dimer complex. In the second example, we can see that the fully methylated derivative of the titanosine dimer was recently synthesized in either at -80 degrees. Prolonged exposure of a benzene solution of the titanosine to dinitrogen at 20 to 25 degrees results in the formation of a complex which can be formulated as a titanosine dimer containing a dinitrogen molecule. Recently, the molybdenum analogues of this type have also been prepared under high pressure condition using dinitrogen gas. In the third example, the isopropyl magnesium chloride can also react with bis triphenyl phosphine trichloroiron under dinitrogen conditions to produce an incompletely characterized complex containing 1 mole of dinitrogen per 2 moles of iron. Grignard reagents have also been used to prepare dinitrogen complexes of molybdenum and titanium. Dinitrogen as a ligand can also displace ligands in a coordination sphere. For example, the aqua pentaligand ruthenium complex can react with dinitrogen where the water molecule can be knocked out and dinitrogen acts as a coordinating ligand. So, dinitrogen as a ligand can also show displacement reactions. A few displacement reactions of dinitrogen complexes are shown in the table, where both monomeric and dimeric products are prepared. This reaction may proceed through the formation of a solvated intermediate. For example, in the reaction shown here, the sodium tetraphenyl borate is forming an intermediate complex with the given complex. The given complex can then react with dinitrogen to form dinitrogen complex. For example, the CP complex of iron can react with tetrafluoroborate anion in the presence of acetone under dinitrogen condition to give a dimeric complex where dinitrogen acts as a bidentate ligand connected with both the iron atoms via an acetone coordinated intermediate. Also, a few low valent olefin complexes will react with dinitrogen if a tertiary phosphine is also present. For example, the complex has been obtained from the many metal acetyl acetonates can also react with dinitrogen in the presence of a tertiary phosphine as a ligand and an aluminum alkyl complex. For example, the diethyl aluminum can react with dinitrogen to show such kind of reaction. Sometimes the product contains a hydride ligand as well as dinitrogen and phosphine. For example, we can see a number of examples that shows. Also, metal amalgams have also been used as reducing agents in place of aluminum alkyls employed in this type of reaction. In this manner, Chart and his group have obtained a large number of complexes which are shown here. Also, Shilov et al. Have reduced a number of ruthenium and osmium halogen complexes with zinc amalgam and obtained several dinitrogen complexes such as the THF based diaqua nitrogen dichlororuthenium. And also the zinc dust is used in the presence of excess phosphine and dinitrogen in THF to reduce various dinitrogen complexes shown here. Moreover, powdered sodium can also reduce various complexes such as cobalt 2 complexes under dinitrogen to give monomeric and dimeric dinitrogen species. A few examples of such kind of reactions are shown here. In the other type of reactions, when molybdenum 3 acetyl acetonate was reduced with triethyl aluminum in the presence of a 10-fold excess of triphenyl phosphine in toluene under nitrogen, an orange color complex was obtained, which is shown as product of this reaction here. This product was empirically formulated as a triphenyl phosphine dinitrogen molybdenum complex. The dinitrogen complex is moderately air stable, whereas the yield of the complex was found to be decreased to 1/5 when triisobutyl aluminum was used in presence of triethyl aluminum. Therefore, the alkyl part on the aluminum also playing a role in the product formation. On the other hand, the complex was not obtained by using trimethyl aluminum. Preparation from compounds containing chains of nitrogen atoms. A variety of ruthenium 3 and 4 and osmium 3 and 4 chloro and amine complexes and even osmium tetroxide will react with aqueous hydrazine to form complexes of the type pentaamino dinitrogen metal dianion. Unfortunately, the products are often contaminated with hydrazine or bis dinitrogen complexes such as the trisphenyl dibutyl phosphine trichloroosmium gives a mixture of starting materials and the corresponding dinitrogen complex, while the tris dithiocarbamate iron reacts with hydrogen to give a unknown product having dinitrogen as the ligand, which was identified by the IR frequency which absorbs at 2054 centimeter inverse. Also, the oxidation of coordinated hydrazine can also take place, which can be produced to form the first dinitrogen complex of manganese. The example is shown here. Intermediates have been isolated and characterized, therefore the reaction has been completely characterized. There are also evidences that this reaction, which is the best way of preparing the pentaamino dinitrogen ruthenium complex, proceeds through a ruthenium 3 azido complex. If cis diene tetraamino ruthenium anion used, the product was found to be different. In this case, the product was tetraamino aqua dinitrogen ruthenium and not the bis dinitrogen complex. Therefore, we can say that the reaction can also be done at pH 0. Binuclear as well as mononuclear species can be obtained. Kane McGuire et al. Have the evidences that dimers of such kind are formed by dimerization of the nitrene complex with the loss of 2 protons. Moreover, the nitrous acid reacts with coordinated azide ligands to give dinitrogen complexes and nitrous oxide. For example, the diarase nitrogen chlororuthenium hexafluorophosphate complex and a mixture of other complexes have been prepared via this reaction. Also, the metal complexes containing dinitrogen can be prepared by this kind of reaction shown here. Another kind of preparation is shown in this type of reaction where the osmium tetrahydride will not react with free dinitrogen even under high pressure conditions. Therefore, many of the systems which react with dinitrogen to give a dinitrogen complex can also react with nitrous oxide and 2O to give the same product. Since nitrous oxide complexes have also been isolated, it is almost certain that these reactions proceed through N-bonded nitrous oxide complexes, which is subsequently reduced to form the dinitrogen complex. The examples of such type are shown here. There can also be preparations in which 2 dinitrogen atoms are combined to give a dinitrogen complex. For example, in the reaction, there is a doubtful because the analogous reaction of diarase nitric oxide chlororuthenium dichloride with hydrazine was found to give a azide complex and not the dinitrogen complex, which was previously believed. However, attempts have been made to apply this reaction to ammonia molecules bound to other molecules such as molybdenum and ruthenium, and these attempts were successful. We can see the reaction. This reaction shown here proceeds probably via an amide complex of the type as shown here. Moreover, the ammonium salts can also react with coordinated nitro ligands to produce dinitrogen complexes of platinum and rhodium containing bridging dinitrogen ligands. And here we can summarize. The dinitrogen complexes are the metal complexes where dinitrogen acts as a ligand by coordinating with a metal ion through one of the nitrogen atom. Dinitrogen complexes are known with few transition metal ions such as molybdenum, iron, ruthenium, and osmium, etc. A large number of dinitrogen metal complexes have been synthesized and applied for dinitrogen fixation or artificial nitrogen fixation reactions. Natural dinitrogen fixation involves reduction of dinitrogen to ammonia and other nitrogen hydrides of higher analogues. Dinitrogen complexes can be synthesized by a number of processes such as by direct reaction with dinitrogen gas or by reaction with compounds containing chains of nitrogen atoms or by methods in which two nitrogen atoms are combined to give a dinitrogen complex.